Okay, so our first talk this afternoon is Alexander Polischchuk, who will speak about moduli spaces of curves with non-special divisors.
Okay, so I'd like to thank the organizers for the invitation. So in this talk, I'm going to tell about some modular spaces of curves. And this is kind of not just smooth curves, but this is about some compactifications of the modular spaces of curves. And this is partially motivated by recent works on alternative compactifications, different from the standard Deligne-Mumford compactification. And I guess there was like an influential circle of ideas from the works of Hassett and others. And but actually, my kind of way to this was through the very last part of the talk, where I'll talk about the relation to the moduli of infinity structures. But I'll start actually with just telling you how to construct from scratch some modular spaces of curves using the very simple idea that you have, if you have a curve and marked points on it, you just take the complement to these marked points and you try to describe the algebra of regular functions on this complement by constructing some special bases there. And so then the coefficients of the product will give you coordinates on the modular space, and then you can write. This is defined after some choice of rigidification. So there is some group acting on it, and then you consider the corresponding JT quotients. So the main point is that in this case that I'm going to consider, it's actually possible sometimes to describe explicitly what kind of curves we're getting. So I want to point out that I'm going to consider no a priori restrictions on singularities of curves. So that's the kind of difference of this approach. So a priori I can get all kind of bad singularities on the curves, but it turns out that once you turn on some stability condition, you actually can precisely describe what kind of geometry you get. So that's kind of the main reason why I'll consider especially the case G equals 1, because there I can completely compute all the stability conditions. Okay, so let's start with this very kind of basic idea. So if you have a smooth projective curve and a point on it, so if you choose also formal parameter at this point, then if you have any regular functions outside this point, you can consider its Laurent decomposition at this point. And so you get some Laurent series, and in this way you get an embedding of this space of functions into the space of Laurent series. And so the corresponding subspace, which I denote by W, it has a very nice property that you can recover cohomology of the original, of the structure sheaf on the original curve from this subspace by intersecting it. So if you want to recover H0, you intersect it with the regular expansions. If you want to recover H1, you consider this quotient. And so because we know this have to be finite dimensional, so we actually understand what kind of subspace we're getting. So this is called Sato-Grassmannian, the kind of Grassmannian in the infinite dimensional space, equipped with this kind of subspace. So you consider this kind of conditions, and this defines for you Sato-Grassmannian, which can be defined in a purely algebraic way as a scheme and of infinite type, of course. And furthermore, like the usual Grassmannian, it has some kind of standard open charts where it can be modeled just by a fine space, of course, infinite dimensional. But that's basically how the coordinates on the modular space will appear. So you kind of look at this W as a point on the Grassmannian. And on the Grassmannian, one has standard coordinates. Yeah, so this is, and one more remark is that you can actually recover the original data, the curve, well, at least in this setting where you have a smooth curve. So you can recover the original data from the subspace in the following way that when you basically, if you have this algebra, so in order to recover the curve, all you need to know, in addition, you need to know the filtration by pole, by order of pole at the point P. And of course, you have this filtration because you can just look at the intersection. So the polar conditions are recorded by this Laurent expansion. So you can you don't lose any information by passing to this W. So yeah, there is a remark that this construction, of course, is well known, and it's kind of plays a role in the construction of the action of Virasoro algebra on the modular space of curves and on some natural line bundles over this. This is studied by many people. So I'm going to consider now, I'm going to generalize this simplest case into two ways. So first of all, I allow n marked points, and so I consider fixed formal parameter at each marked point. Then you can expand at each of these points, and you get embedding into this direct sum. So this is still a point of the appropriate Sata-Grassmannian. But more seriously, I'm going to allow my curve to be singular. So and of course, this construction really doesn't fill it almost. So the only thing you care about is that the curves, the marked points themselves, are smooth, because you want to be able to expand in Laurent series near these points. And so all I assume is that this is reduced, connected, singular so possibly singular projective curve. But in order to be able to recover the curve from this data, I also have additional assumption here, which is very important. I assume that this line bundle defined by these marked points, is ample. So what this really means is that on every reducible component of my curve, I have at least one marked point. So there's really no condition if the curve is irreducible, but if the curve has several components, there should be at least one marked point on every component. So this kind of is an important feature. So the kind of compactifications I get from this construction are always going to have this property that they will classify only curves where there are no unmarked components, which is, of course, not true for the Lin-Mumford compactification. So you can imagine that there will be some kind of birational contraction of the loci where you have unmarked components when you pass to this birational modulus. All right, so now I define formally the moduli problem. So the moduli problem is that I consider a curve of arithmetic genus G with smooth marked distinct points, and I assume that this divisor is ample. So I explained it just means that on every component there is at least one marked point. And so now I add one more condition. I add the condition that this divisor is also non-special. So this means that it has the expected number of global sections. So in other words, there is an expected number of rational functions with poles of order at most 1 at this point. So the expected number being given by Riemann-Roch formula. So this is kind of a technical, in some sense, it's a technical restriction, but it actually places me into, when I consider the corresponding point in Sata-Grassmannian, it places me into nice union of open charts and kind of helps me to get the canonical basis in the space. So along with this modular stack, I also consider two kind of rigidifications of this space where I choose some additional data. So the one I already discussed before. So this is where the biggest one is where we just choose formal parameters at every marked point. But there is an in-between choice, which is still finite dimensional, where we just choose non-zero tangent vectors at each point. So I kind of break this up into two steps. So there is this torus fibration where I just choose non-zero tangent vectors, or I can actually go to the full formal parameter at each point. Yeah. So this condition by Riemann-Roch formula can only be satisfied when n is at least g. So this is a kind of limitation on this way of constructing the compactifications. There is, however, a modification of this procedure where, so here I kind of put weight 1 to each point. So instead I could, for example, consider some integer weight, non-negative integer weights assigned to each point such that they sum up to g. So that's one case at least where I know how to do it. And then you can also get some interesting compactifications when n is less than g. But in this talk, I focus on this case where n is bigger than or equal than g, and I consider the condition that this divisor is non-special. So one example which is easy to understand is the case when G is 0. So then the restriction on H1 is empty, and the only restriction you really have is that there is at least one marked point on every component. And this modular space has been considered before. So it's actually an example of, so it's called sometimes Bodji-Kontsevich compactification because it coincides with this topological compactification which was constructed by Kontsevich actually for arbitrary G. So in his famous paper on intersection theory and area functions, he considered, so what you do is you consider the Deligne-Mumford compactification, but then you introduce some equivalence relation which basically contracts the unmarked components. So you say that two curves are equivalent if after you contract marked components, they become the same, and also kind of topologically they look the same. And so in the case of genus 0, this construction actually can be made into algebraic variety. This was done by Bodji. And so this is precisely the space. I'll actually talk a little bit more about this space, about this example. So now returning to the general case. So there is an HL map from this modular stack. So now I'm working mostly with this intermediate stack. So this tilde on top means that I choose tangent vector, non-zero tangent vectors at each marked point. So I have not necessarily smooth curve of genus G. So I have this n marked points and non-zero tangent vectors at each point. So then there is an HL map from this modular stack to the finite dimensional Grassmannian, to the Grassmannian of n minus G subspaces in n-dimensional space, and it's defined as follows. So there is a short exact sequence of coherent sheaves on a curve. So here actually it's a mistake. This should be tensored with the skyscraper sheaf at the point pi. So then from this, because H1 of the middle term is 0, so it leads to this surjection from the n-dimensional space, sum of tangent spaces at each point, to H1 of O, which is a G-dimensional space. So we get a surjection from n-dimensional space to G-dimensional space. So the kernel of this surjection is the point of Grassmannian. And because we chose trivialization of the tangent spaces, this can be just identified with Cn. So we get a point in the Grassmannian. And so this is, so Grassmannian, of course, has the standard covering by open charts. And so the preimages of these opens can be described by this condition. So the condition, so we had in the beginning the condition that the sum of all points was non-special. But in fact, there is always some, you can always choose G points out of these n points, such that already some of these G points is a non-special divisor. So this is something which you can only do when the weights you put here are all 1. So all right, and now the theorem is so there's several parts about so several statements about this modular problem. So first of all, if you kind of take maximal additional data, so if you also choose here the formal parameters, then this infinite dimensional space embeds into Sata Grassmannian, and its image actually can be described explicitly. It's just a closed subset of certain open subset here. So this condition is really an analog of the condition that I considered non-special divisor. So there is some open locus in Sata Grassmannian. And the equations that define my modular space in this open locus are just the equation that I get a subalgebra. So remember that the Krichyver map associated to a curve, the corresponding algebra of functions regular outside the point, viewed as a subspace in the Laurent series. And so this actually can be easily made into explicit equations in terms of coordinates on the Grassmannian. So this modular space is therefore so kind of described by explicit equations here. But we want to now get down to finite dimensional modular space. So we have this action of the group of formal of changes of formal parameters. So, and remember, this group is not the full group of changes, but only changes that do not change the corresponding tangent vector. So I can change the formal parameter, but I do not change its one jet. Okay, and so this group, it turns out that it acts on this smooth, on this open locus in Sata-Grassmannian. The action is just free, and in fact, it even has a very nice section. So at least locally, so you can cover the this open set by some open charts, which are isomorphic to infinite dimensional affine spaces, and the quotient by this action, by this free action, is also going to have finite open covering by infinite dimensional affine spaces. So this actually gives you, so when I quotient out here by this group, I just get this modular space where I have a choice of non-zero tangent vector at each point, and therefore I realize it as a scheme of finite type, which actually turns out to be affine over this Grassmannian. So then there is a remaining action of the torus, because I can still rescale the non-zero tangent vector. So I'm kind of really going to then study this torus action, the corresponding JT quotients. And so there is an additional nice feature of this action, that there is a copy of diagonal C star in this torus. And with respect to this, so of course this C star to the end, this torus also acts on the Grassmannian in the standard way, and the diagonal acts trivially here. So it turns out that there is a canonical section of this projection, which from this modular space to the Grassmannian, which consists of C star invariant points. So these are some special curves, which are all actually singular, but they're points in this modular space. And so C star action turns out to have positive weights, well, not negative at least weights on the fibers of this map. Yes, and so now what we want to do is we want to consider JT quotients with respect to this action here, and in this way we'll get some birational projective modules of MGN. So let's consider a very, very simple, very basic example. So if G equals N equals 1, so just consider elliptic curves with one point. So then, so we all know that when you have an elliptic curve and you subtract a point, and the same works actually if you just have an irreducible curve of genus 1 and you subtract a non-singular point, then you can actually find two special generators of this algebra, which one has a pole of order 2, another has pole of order 3, and so you have a little ambiguity in choosing this basis, but you can fix this ambiguity uniquely by requiring that the following equation holds, which is called the Weierstrass normal form. And so in this way, you see that this modular space with the choice of non-zero tangent vector at the point P is just going to be a affine space A2. So then the C star, of course, acts on it, and it is going to rescale P and Q with weights 2 and 3. So yeah, the unique invariant point in this case is just P equals Q equals 0, which corresponds to the cuspidal cubic. So okay, so let's consider now another example, which is when G is equal to 0. So in this case, so you also can consider a special basis. So in both of these examples, there is no Grassmannian. So the modular space with the choice of non-zero tangent vector is just an affine scheme. So this means that I'm just going to get some coordinates on the modular space, which will be subject to some equations. And so this also, in this case, it also corresponds to choosing some special basis of this algebra. So what special basis do you have here? So here simply, because the genus is 0, so actually there is, for every point, there is actually a function which is regular outside this point and has pole of order 1 at this point. And so it starts like this. So I mean, normalize it by, because we have a choice of a tangent vector here. So the only ambiguity is that we can add a constant to each xi. But in any case, they form a generating set for this algebra. And furthermore, it's easy to see that defining relations are quadratic of this form. Simply because when you take xi times xj, you know that this is a function which has poles of order 1 at pi and pj, and we already have a basis of functions which are at most with poles at pi and pj, namely these three functions, xj, xi, and a constant. They already form a basis there, so therefore there should be such a relation. And then you figure out that there should be further constraints on this in these coordinates, and they are all actually just can be written by this unique relation. So this is actually a lot of relations, because you see that there are indices k. There's index k on the right-hand side, and there is no index on the left-hand side. So you get actually quadratic equations on these coordinates. And if you normalize them like this, then you can fix the ambiguity of adding constant to xi. So you actually get a very explicit scheme just defined by quadratic equations. Yeah, and by the way, so there is a special point there, as usual. So the point which is invariant under C star action is the point where all these coordinates are 0. So then all the right-hand sides here are 0. So you just get equations xi xj equals 0, which is just the coordinate cross. So this is a curve with n components, which all intersect at one point with independent tangent vectors. And so, in fact, the same modular space can be recovered if you just consider this singularity, which is called rational m-fold point. So if you consider this singularity, which is the coordinate cross, and then you try to write its universal deformation, then you get precisely the same affine modular space. Yeah, and so so this is the remark. So actually, the only singularities that you can possibly have in genus 0 are this so nodes and kind of higher coordinate crosses. So you can have coordinate. So there's always some intersection of components with independent tangent vectors. That's the only singularity you can have. So yeah, so then you can consider the corresponding JT quotients. So it turns out that there is only, so there is kind of one interesting chamber to look at where, so as usual in JT theory, so because this is a affine space, so we just consider trivial, so as a polarization, we just take trivial line bundles, so it all comes to choosing a character of the group, of the torus. So this character is given by some parameters here, a1 to an. So there is one interesting chamber where to consider JT quotient, and also on the walls of this, on the boundary of this chamber, you also get something interesting, and away from it, you get empty. So we then consider the corresponding, if we consider the corresponding stable points, so where all of these are positive, so then this just turns out to mean that we require that every reducible component has at least 3 special points. And special points here means either a singular point or a marked point. And this is exactly what Bojji-Kontsevich space parameterizes. So it parameterizes points which can be obtained from a stable curve of genus 0 by contracting unmarked components. So they're all going to have this property that every reducible component has at least 3 special points. And in fact, the same space can also be described as follows. So if you take mgn bar, you can consider the line bar, sorry, m0 n bar, so genus is 0. You can consider the sum of all psi classes at all the marked points, and then this defines some projective embedding, and so this is actually the same, the image, some map to projective space, and this is just the image of this map. So yeah, and so the previous equations that I had on the previous slide, they actually, if we view them as, so these equations here, if you view them as equations on homogeneous coordinates alpha ij, which should be viewed as coordinates in the product of projective spaces, then you just get precisely equations for this Bojji-Kontsevich space. Yeah, so one kind of scandalous thing I discovered in kind of thinking about this and asking people around is that even though kind of this modular space is kind of well understood if you as a topological space, it actually, if you view it as a scheme, it's not known for sufficiently large n whether this is a nice scheme. So whether it's normal or even whether it's reduced, it's not known. So it's somehow, so Bodge actually claimed it in his paper, but his proof doesn't work. So this is an open question. All right, so now I move to the case G equals 1. So in this case, first of all, I want to describe so what kind of curves we can encounter possibly. So because this is genus 1, we still kind of have a pretty good understanding of what kind of singularities the curves can have. So I claim that, so I'm still working with this space where I choose non-zero tangent vectors, which means that I'm kind of considering more kind of more curves than I would have later when I only choose stable ones. So any curve of genus 1, which corresponds to a point in this modular space, turns out to have a very special decomposition. So there is one component there of arithmetic genus 1, which I will call a minimal elliptic component, and then there are some rational curves of arithmetic genus 0 which are attached to it, but not to each other. And so this minimal elliptic component, it actually can have, it can be a smooth elliptic curve, but it can also be of several other types. So it can be a nodal genus 1 curve, so it can be a cycle of projective line, and this also includes an irreducible nodal curve. But there is also one more type of curve that can occur, and this I call elliptic M-fold curves. So these are the following guys. So the elliptic M-fold curve, so when M equals 1, this is just cuspidal cubic, so just a curve of genus 1 with one cusp. If M equals 2, then what you should have is you should have two projective lines which are tangent to each other at one point. So this can be realized as a union of cubic and a union of conic and a line in the plane. And for bigger M, so what you can have is you can have M generic lines which pass through one point in M minus one dimensional space. So for example, M equals 3 corresponds to the 3 lines in P2. So M equals 4 corresponds to 4 lines in P3 through one point, and so on. So what's interesting about this types of curves is that these are precisely genus 1 curves which are Gorenstein and which have trivial dualizing sheaf. So this turns out to be equivalent to be one of these types. But then now the more general curves that occur here is that I can have one of these curves like this, and then to this curve I can attach transversely at distinct points some rational genus 0 curves, which are like we described before. So like we considered in the case G equals 0. So they can be just, so this rational tails, these are just trees of P1s, which can be connected not just by nodes, but some coordinate crosses. But furthermore, one other thing which is kind of vastly different here than in the Deligne-Mumford computation is that I allow the points of attachment to be singular. So I can have a picture like this. So I can have, is there a choke here? Oh, yeah. No, there is no choke. Anyway, so you can have a cuspidal curve, for example, and then you can have, E could be, for example, a curve with a cusp, and then this rational component can pass right through this cusp, but with independent tangent vector. Or you can have actually R could be maybe thanks. Yeah. Yeah, so you can have pictures like this. You can have a cusp, and then you can have some kind of rational curve attached to it and intersecting it transversally in several points. So you can have So rational tail just looks like the tree of projective lines, which all intersect in this coordinate crosses. But it can intersect, so this is E, and this is this whole thing is just R1. And then there could be, for example, R2 here. Okay, and so now I can describe precisely which of these are stable with respect to different JT stability conditions. So now on this space, we have the action of the torus. So if you fix a character of the torus with some, so now I fix a rational character. So now this time the modular space is not going to be affine. So it's genus equals 1 and n is big. So this corresponds actually, this modular space has a map to projective space, but it's affine over projective space. So now I'm going to consider polarization, which is a pullback of O of 1 from this projective space, and then tensor it with some character of the torus. So now I fix some rational character of the torus, and so I can completely describe when such a curve is going to be stable with respect to this character. And the description depends on the following. So given such a curve, and so there are some marked points in it, and remember there's at least one in each component, then I can define some subspaces. So roughly, first of all, I can consider there are two kinds of marked points, those which lie on this elliptic component, and those that do not lie. So I denote I. This is a subset of marked points which lie on elliptic components. So among those which do not lie on elliptic components, I only actually care about the marked points such that there is at least 3 special points on the component containing them. And then there is among the curves which lie on the elliptic, among the points which live on the elliptic component, I actually pay special attention to those which have at most 2 special points in the case when E is not nodal. And so then there is a theorem which completely describes the semi-stability condition in terms of this subset. So the sums of the weights AIs which define the character, which are just rational numbers. So it should be at least 1 if I sum over all points which lie on the elliptic component. It should be smaller than 1 for this smaller subsets. And all these JT quotients are projective, and so they all give birational projective modulus of M1n. So there are 2 particular cases I want to point out. So one case is if I consider the chamber where all AIs are bigger than 1. So the stability behaves, again, kind of similar to, in some way similar to the case G equals 0. So the condition is stability simply becomes the condition that there is at least 3 special points on the normalization of every rational component. And this is, again, equivalent to the fact that this curve is obtained by some contraction from the Lin-Mumford stable curve of genus 1. So, and another example is where I consider the character where all weights are the same, and they're in this interval between 1 over n and 1 over n minus 2. Then the stability means that in this decomposition of the curve into elliptic part and rational tails, I actually don't have any rational tails, so this completely forbids to have rational tails, and the curve just has to coincide with its minimal elliptic component, which is equivalent to the condition that that every point is actually defines a non-special divisor. So it turns out that the points which do not lie on the minimal elliptic component, they never define a special divisor. For them, H1 will be non-zero. But if all points lie on the elliptic component, that's precisely the condition that they are all non-special. So we call such curves strongly non-special, so where every marked point is non-special. So I pointed this out because both of these modular spaces appeared before, so they were both constructed in 2 different works of David Smythe. So the first one, actually, he constructed for arbitrary, so kind of this is similar modular space for arbitrary genus. And the one in the example 2, so this is actually the modular space which we studied in a joint work with Yankee Likile in great detail. And actually, we were able to show more were able to study it in more detail, what kind of geometry we have. And this is actually based on the next slide, where you can, again, in this case, you can find a very, very explicit basis of the corresponding ring of functions away from these marked points. So namely, this time you can consider, so now genus is 1, so in order to have some interesting rational functions, you have to fix 2 marked points and allow poles there. So then you have the corresponding unique functions up to adding a constant. You normalize them by some residue condition. And then you can, so you pick sufficiently many of such. And then again, you get pretty simple defining equations for the curve. And then you can also write explicitly, so the coordinates here become coordinates on the modular space. And you can write explicitly the equations on them. And so one remarkable thing that happens here is that the modular space so this is still modular space where I choose, so yeah, instead of choosing tangent vectors, in this case, it's enough to just choose one global non-zero section of the dualizing sheaf. So instead of considering kind of n-dimensional torus, I can just rigidify this problem by one-dimensional scalar here. And so it turns out that in this setup, the modular space for m plus 1 is precisely the universal curve for the modular space of n. So this becomes wrong once you introduce stability conditions, but before introducing stability conditions, this turns out to be true. So this affine modular space coincides with affine universal curve over the previous affine modular space. And this is exactly what we use to prove various geometric properties, because we know that all the curves that it parameterizes are Gorenstein, so we can kind of prove a lot of nice properties of geometric properties just using this by induction. Okay, so now I pass to another special case where n equals g. So in this case, we again have a affine modular space because, again, there is no interesting Grassmannian here. So here, if I just consider g marked points such that the corresponding divisor is non-special, then again, you can pretty easily construct a special basis in the functions which are regular away from the curve. And actually, this basis looks a little bit like the basis we had in the case g equals n equals 1. So for each I, we kind of construct rational functions which are allowed double or triple order pole at this point, and which have only order 1 pole at all the other points. And so then this algebra is generated by these functions. And furthermore, there is actually a natural basis just by x, powers of x and powers of x times y. And so you can fix uniquely the ambiguity. And this is, again, pretty similar to the case to the case g equals 1. And you can even try to write the corresponding equations of the universal curve. They will already look a little scary. So here are the equations of the universal curve. But what's important here is that you can actually pinpoint the coefficients which become generators on this module, which become coordinates on the modular space. So they generate the functions on the modular space of such things. And so because you know what their weights are, this actually allows you to say something about JT quotients. So yeah, so what I say here is that every other coefficient in these equations can be expressed in terms of the red ones. So you can more or less describe explicitly the corresponding affine scheme. And so when you then talk about JT stability, so the weights of these coordinates tell you what is the wall structure for the stability. So you know that it's going to be related to this special set of vectors. So here the situation is more complicated than in the case g equals 1. And so even though I can say something about stability there, I do not know how to describe precisely what is going to be stability in this main chamber. So the main chamber is where I consider character, where all these weights are positive. So I know that it doesn't matter then what weights you take. So there's going to be just one stability condition, but it would be very interesting to describe it explicitly. So maybe it's again related to this Smythe modular space. for general G. So finally, I'm going to say a few words about how this is related to moduli of A-infinity structures. This is something completely different, but actually this will be related to what I said before in the next slide. So this is a quick reminder of what is an A-infinity algebra. So if you have a graded vector space, you should have a sequence of operations which include the differential M1, which is of degree 1, M2 is a double product, M3 is a triple product of degree -1, and so forth. And there are identities here which generalize associativity equations. So here, basically, the bracket of Mi and Mj means that you can sum over all ways to insert Mi as one of the arguments for Mj, and vice versa. So you can insert Mj as one of the arguments for Mi, and sum over all ways of doing it. This is called Gersten-Haber bracket. So then if you given some finite dimensional associative graded associative algebra, you can then try to classify all possible extensions of the structure to the A-infinity algebra structure. So namely, I'll consider just M1 to be 0 and M2 to be the given product on this associative algebra. And then I can start looking at what are possible M3, M4, etc., which make it into an infinity algebra. Of course, this is going to be some infinite dimensional affine scheme, right? Because these tensors, they're just given by the coefficients, and so this will give some quadratic equations on this coefficient. So this is some infinite dimensional affine scheme, but there is an equivalence relation which is like homotopy between these infinity structures. So there is this infinite dimensional unipotent group of gauge equivalence we checked on it, and so basically when you consider this modulus, this quotient, it has much more chance to be finite dimensional, and sometimes it is. So there is a theorem that so even though this action is usually very non-free, nevertheless the quotient is often a nice space. So under some assumption on Hochschild homology of the algebra, you can prove that this action actually admits a section, and this section is just a closed subset, so a closed subscheme in this affine scheme. And so this becomes this realizes this quotient just as an affine scheme again. And under some further assumptions on Hochschild homology, it becomes finite dimensional. So now, what's the relation with moduli of curves? So if you are given a curve like I described before, so now I'm concentrating on the case n equals g, even though this can be generalized to n bigger than g. So if you have a curve with g points such that these points form a non-special divisor, then this actually makes the x. So I consider a special coherent sheaf, which is a structure sheaf plus the sum of skyscrapers at these g points. And so then the X algebra of this sheaf turns out to be very pleasant. So it actually does not depend up to an isomorphism on a curve. So because for every so it's generated by the following elements. So for every marked point, you have an obvious map from structure sheaf to the skyscraper, and you have, by third duality, you have a degree 1 map back. But now the point is that if I start here and I go to the marked point and then go back by degree 1 morphism, if I compose this, I will be getting various elements in X1 from O to O, which is the same as H1 of O. And the condition that the curve, that this formed a non-special divisor, is precisely the condition that these compositions are linearly independent. And so therefore, from this composition, I just get the basis of H1. And this basically explains why I get a nice algebra. So it's just described by these generators and some natural relations. But actually, in order to fix the isomorphism of this E with the fixed algebra, I precisely need this choice of non-zero tangent vectors, because this will trivialize the spaces X1. Okay, so then, but it's known that when you have some derived category and you consider some X algebra in derived category, it actually comes equipped with some higher structure. So in fact, it's a cohomology of some natural differential graded algebra, and therefore by something called homological perturbation, in fact, on this Ext algebra, there appears a canonical infinity structure, well, canonical up to equivalence. And so in this way, we get a map from the modular space of curves to the modular space of A infinity structures on this fixed algebra. And the kind of amazing fact is that this map is, in fact, an isomorphism. So, and the remark is that there is a similar interpretation for n bigger than g, but in this case, because you have more points, actually the M2 is also going to vary. So you'll have a slightly different setup for this modular space, but it also works. Okay, so my last slide is just references. Thank you.
Are there any questions? Is it possible to go back to the slide before and explain slightly more slowly the key points at the end there?
So yeah, so maybe I can give a couple of words on the proof of this theorem. So there is the important part in the proof is that there is a C-star action on both spaces, and so this modular space that you have for on the left, this UGG tilde and S. So this is actually can be thought as a universal deformation of the most singular curve you have there, and the most singular curve is the following. So you take union of genus 1 of G copies of the cuspidal curves of genus 1, and they're all attached at the cusps. So you take kind of transversal union of G cuspidal curves. So this has arithmetic genus G. And so basically, if you understand deformation theory of this curve, then you understand this modular space. And so what's nice about this curve, so on each component, you choose a point at infinity. And so this turns out to be the only C-star invariant point of this modular space. So this curve actually has a C-star action. And because it has a C-star action, you can prove that the corresponding infinity structure is trivial. So under this map, this goes to the trivial infinity structure. Trivial means that higher products are all 0. So M3 and higher are all 0. So then what you also can find out is that the weights of C star on this affine modular space, they're all going to be non-negative. So this whole modular space is contracted by C star to this unique point. And the same is true on the other side. So once you understand deformations of very, very special points, you actually understand the whole modular space. And the deformations are well known, there are well-known theories of deformations for both infinity algebras and for varieties, in particular for curves. So that's how this theorem is proved.
Okay, so if there are no more questions, maybe we can thank the speaker for his nice talk. The next talk will be in 12 minutes' time. It's Laura Shaposhnik.